Yeah. Okay. All right. Section 9.3, special right triangles. We're going to talk about two special right triangles today. They're special because they have special characteristics. Right? We've been talking about applying the Pythagorean theorem to right triangles. The Pythagorean theorem only applies to right triangles, and it will continue to apply to right triangles. But we're going to look at some shortcuts of some special right triangles. All right, so Hollywood. Mr. Grande informed us earlier in 7th period, Technicolor, is that what it's called? Yes, sir. The first movie made in Technicolor was The Wizard of Oz. And The Wizard of Oz is the basis for today's lesson. How many of you have seen The Wizard of Oz? Very good, all of us. All right. So I'm sure you've all seen the part where Scarecrow gets a brain, right? Yeah. Let's take a look at how Scarecrow gets a brain.
Where men go to become great thinkers, and when they come out, they think deep thoughts, and with no more brains than you have. They have one thing you haven't got, a diploma. Therefore, by virtue of the authority vested in me by the Universitatis Comitiatum e Pluribus Unum, I hereby confer upon you the honorary degree of Ph.D. Ph.D.? Doctor of Ecology. Sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Oh, John! I've got a brain! How can I ever thank you enough? When you can.
The Scarecrow said the sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Was the Scarecrow correct? Did the wizard give him a brain? The Scarecrow just happened to be completely incorrect in what he just said, right? Now, how do we fix this? The sum of the square roots of any two sides. Well, that's not what the Pythagorean theorem starts out by saying. The Pythagorean theorem says the sum of the squares, not square roots, and not of any two sides, but of the legs of an isosceles triangle, not just any isosceles triangle, but an isosceles right triangle, is equal to the square root, not the square root again, is equal to the square of the remaining side, and we know that remaining side is called the hypotenuse. So, unfortunately, the wizard did the Scarecrow a disservice, unless his intention was to show the Scarecrow that handing him a diploma made him no more intelligent than he already was. Which is probably intelligent enough because they got all the way to Oz, right?
Yeah.
Yeah. All right, but we need to be more intelligent, that's for sure. Which means we need to investigate isosceles right triangles. So to figure out this conjecture, we're going to take, I bet all we need is maybe 3 isosceles right triangles. So I'm going to draw 3 isosceles right triangles up here. And if we're filling out the table, I think the first one said the length of the legs was 1. The second one, the length of the legs was 2. And the third one, the length of the legs was 3, right? So I bet you after these 3, you'll see the pattern. So we have to find the length of the hypotenuse in each of these. Well, we'll just apply the Pythagorean theorem, right? So here we have 1 squared plus 1 squared equals c squared. 1 squared is 1, so 1 plus 1 equals c squared. 2 equals c squared. Take the square root of both sides, and the hypotenuse equals the square root of 2. Our second example, isosceles triangle with the legs equal to 2. So I have 2 squared plus 2 squared equals c squared. 2 squared is 4, so that's 4 plus 4 equals c squared. 4 plus 4 is 8 equals c squared. Take the square root of both sides, c equals the square root of 8. And simplifying radicals on last night's homework, we know that this can be the square root of 4 times 2, and the square root of 4 is 2. So that's 2 square roots of 2. equals c. Right? 2 square roots of 2. In our third example, an isosceles triangle, or isosceles right triangle with legs equal to 3. So again, apply the Pythagorean theorem. 3 squared plus 3 squared equals c squared. 9 plus 9 equals c squared. 18. Take the square root of both sides. Simplify the square root of 18. 9 times 2. Square root of 9 is 3. 3 square roots of 2. So the pattern is that whatever the length of the sides is, take that times the square root of 2, and you end up with the length of the hypotenuse. Whatever the length of the sides are, take that times the square root of 2, and you end up with the length of the hypotenuse. Whatever the length of the sides is, take that times the square root of 2, and you end up with the length of the hypotenuse. So to complete the conjecture, in an isosceles right triangle, if the legs have length L, then the hypotenuse has length L times the square root of 2. So the next special right triangle we're going to talk about is a 30-60-90 right triangle, also called a 30-60 right triangle. And it's formed by bisecting any angle of an equilateral triangle. So down below here, we can see that we have an equilateral triangle right here. And we are bisecting it from top to bottom, right? We're cutting it in half. And what do we end up with? We end up with a top angle of 30 degrees. The bottom right angle is still 60 because we didn't touch it. And of course, when we cut it, we created a perpendicular. So that third angle is 90 degrees. Now, the 30-60-90 triangle shows up in math a lot in engineering because it's half of an equilateral triangle. So it's a valuable triangle. But we want to investigate the relationship between the side lengths of this 30-60-90 right triangle. So again, I'm going to give you a few minutes in your groups to work through this investigation. Fill out the table as much as you need to see the pattern of the shortcut for finding the sides of a 30-60-90 right triangle. So again, in order to do this investigation, we need to take a look at some examples, and I think 3 examples will be enough. So each of these is a 30-60-90 triangle. Obviously, the top angle is the smallest. This is our 30-degree angle in each, and this is our 60-degree angle in each, right? And in the table, they first tell us that the shorter leg is 1. The shorter leg is obviously opposite the smaller angle. Keep that in mind. So that's 1. Well, since the 30-60-90 triangle is half of an equilateral triangle, we know the hypotenuse is 2. Now we can use the Pythagorean theorem to find the missing side. So I'll call this A. A squared plus B squared equals C squared. And now I solve for A. A squared plus 1 equals 4. Subtract 1 to the other side. A squared equals 3. Take the square root of both sides. A equals the square root of 3. So I have square root of 3 here. Now we go to our second example. And in the table, they told us the shorter leg was 2. Remember, shorter leg is opposite the smaller angle, so that's the shorter leg there. Well, I know that the hypotenuse is a side from the original equilateral triangle, so this would be 4. And now I have to find that other leg. So I use the Pythagorean theorem again. So A squared plus B squared equals C squared. A squared plus 4 equals 16. Subtract 4 to the other side. A squared equals 12. Take the square root of both sides. A equals the square root of 12. And now we need to simplify the radical, just like in last night's homework. A equals the square root of 4 times 3. 4 is the perfect square. The square root of 4 is 2. 2 square roots of 3. So now we have 2 square roots of 3 here. Let's do one more to make sure we recognize the pattern here. We'll make the shorter leg 3. If the shorter leg is 3, we know the hypotenuse is twice that, 6. And we have to find the other leg with the Pythagorean theorem. So a squared plus b squared equals c squared. A squared plus 9 equals 36. Subtract 9 to the other side. A squared equals 27. Take the square root of both sides. And now, simplify the square root of 27. We know that that is 9 times 3. And the square root of 9 is 3. So now we should be able to see this pattern very clearly. Take the shorter leg and double it to get the hypotenuse. Take the shorter leg times the square root of 3 to get the longer leg. Take the shorter leg, double it to get the hypotenuse. Take the shorter leg times the square root of 3 to get the longer leg. Take the shorter leg and double it to get the hypotenuse. Take the shorter leg times the square root of 3 to get the longer leg. It happens like that every time. So the conjecture in the 30, 60, 90 triangle, if the shorter leg has length A, then the longer leg has length A times the square root of 3, and the hypotenuse has length 2A. So we've learned about the two special right triangles, an isosceles right triangle and a 30, 60, 90 triangle. And they're special because they have these special characteristics, which we've just conjectured, that can be shortcuts to finding the sides of those triangles instead of always having to apply the Pythagorean theorem.